last time we had some problems. If you remember, we had some problems in working with virtual environment in order to install and use by Geo, with some sudden and unexpected error. The first time, the first thing I did yesterday was to simply restart from scratch with the virtual machine. That's because I managed to modify something in my copy and probably alter something. Anyway, doing that, I solved the problems by creating a new environment as explained. So I'm now in the activated environment. I can deactivate and reactivate by recalling the activator script. Okay, so at this level, I mean, in the Bash shell, there are no problems with PyGeo. Simply by running the script you already know, that is this one for Geo 16. But this is not enough. That's because here, if you have a look to the current syspath, you see that we have this one. Okay. So we have in a certain position the internal library path for VM, our current virtual environment, in a certain position. Here the order matters. So if you try to change this order, you could have problems because you could find other packages that have a priority in the order of the path analyzed, and so load the first where you find any of the package that you are looking for. So for syspath, this is important. Now, the problem is instead with notebook, this environment, and it's because if you go to do the very natural thing that is in this case, simply execute exactly the same script to activate our virtual environment, and then execute Jupyter Lab, apparently it's all okay, but it is not enough. That's because, and this is the reason for a trick, the syspath is changed. Let me see what happens. This is exactly the same import sys and print of syspath here. And you can see that this syspath is different. That is the missing VM. Also, there's something prepended for some reason. That is the current, explicitly the current directory where I'm running Jupyter Lab. All the rest seems similar. So the easiest thing to do is simply override syspath, which can be simply used, which can be simply done by simply copy and paste what I show you here. Here, this is a simple string, except the same string I copied here. So when you do this, you change the syspath with the right one. Note that we have VM lib python 3.10, which is the right thing to do. Now, if I try to run this stuff, it's okay. Now, this problem is equally the same for all the scripts that use PyGeo, but in general could be a problem within the notebook of Jupyter Lab for any script that is based on the running of the virtual environment before running the notebook. So it needs to be done before going in the Jupyter Lab. Also, you will miss some packages or another. I will also note that per default there's a .local in your home where a lot of packages could stay. That's because of the history of your installation for Python. Just for as an example, if you have a look here, so in my home, the local label Python 3 site packages, you see that there are quite a lot of things here. So you have part of your setup package, part of your packages within your local label, which is a general one, I say, and part within the virtual amp. Of course, when you install things within the virtual amp, it's a check before proceeding if a package is already present or not. And already present, that means if present in your own user .local library, or in the general, so the system library, which is one of those one. These packages, user local lib, and so on. All this is definitely almost the same even for Windows or for any other system. So you have always to check and verify that your environment is completely coherent. That's because virtualenv generally is thought to work in a very simple workflow. I mean, when you have to use some stuff, when some package, generally we are talking about running a simple script and enter the virtualenv before running the script at command line, not executing a whole environment like the Jupyter Lab, where a lot of things can be done to support multiple objects, multiple systems with quite complicated systems, and which could change the setup of your Python session. So the easiest thing to do is simply doing this. It's not the most elegant way to doing this thing, but currently it's the best one. I'm quite sure that last year, this is the current version of Jupyter Lab. I'm quite sure that last year with Giuseppe we had not this type of problems. So you had only to execute the virtualenv and go to have all working without problems. So if you try to replicate this thing, I'm quite sure that this set of paths is coherent with your own setups settings. But anyway, it's better if you check by simply using the Python 3 interpreter if yes this part within the virtual environment is the same. That's because it depends on the history of your installation. So it's specifically true for your own laptops or your own machines, because this content could change. So it's better to simply use the right one you are currently going to use in a simple shell, and then replicate this within this session. If you all guys, if you all of you try to replicate these things, it could be better, because we can verify if this solves definitely all the issues with specifically PyGeo, but even probably future packages to be used.
I have a question.
Yeah.
In for using Google Colab, is there a way to install PyGeo there?
In the Google Colab, I'm not sure. I don't know. Probably Giuseppe can answer to that.
It's not really straight. It will be quite because in Colab you can do the apt install and installing with apt install all the packages that are already there, but some you need in the installation procedure PyGeo, you need to compile it.
Yeah.
Compilation, some of them are with the sudo write. And
Right.
I don't think that is so easy to do it. You can give a try. You can open the install script that installation of SGeo PyGeo 16 or that Francesco has been modified. Everything that
Yeah.
we apt install is fine. You can do it in Colab, but all the rest you need to play and see what you can do it.
Okay.
Right. So this installation script is a mix of stuff installed by apt-get, apt, and stuff installed by via pip. So this is generally what is done when you have to mix together stuff that is very system related and other stuff that are simple native packages, what I called native packages last time. And so it's better to verify before proceeding. Note that it is quite generally all those operations that are generally we as maintainers or staff on our distributions take care of, because it's not so straightforward for the common user. So the best thing to do will be providing a package, a Debian package in the regular archive, and so also in Ubuntu, and aiming to install PyGeo just by apt, which is the straightforward manner to support usual common people to common users for those kind of things, which are quite tricky or could be complicated. Any one of you did already tried to install PyGeo from the last time you saw this script or not?
I succeeded the last time.
Okay.
And it's still working.
And it's working also within the notebook?
Yes, but I have changed in the upper right of the notebook. There is the kernel. I changed the kernel to VMV. And
okay. That's the other way. Okay, there's the possibility to change the kernel and start a different kernel that includes the kernel. That should be the definitive solution when one has to work with virtual env within those kind of environments. Anyway, things changes from one version to another of Jupyter Lab and so on, and so it could be anyway. It's better to understand what is the basic problem. That is the management of the syspot. When one has to work with those kind of tools, and aiming to the possibility to fix things without aiming to work with settings and so on, which could be not so immediate on the basis of the specific tool one has to use. So let's go with all the rest of the information. So what is PyGeo? PyGeo is it's a relatively new stuff written partially in C++ as for the PK tools and partially in Python. So this is the work of Peter Kempness about trying to simplify the workflow in order to use exactly the same possibilities that PK tools gives to users, and also adding some additional features in order to perform, for instance, classification and other things. It is based partially on the same libraries that are used within PK tools, but it has a lot of stuff that is required to cope with multiple packages present in the Python ecosystem, and specifically geospatial ecosystem. So this is an interesting article that presents the rationale and a description of the at high level of the PyGeo stuff. There's also the possibility of to see a documentation. For some reason, there's this meeting. Well, this is a word by Zoom. I don't know if you see that. Anyway, there's a message for me that it precluded the possibility to click on this tab. Anyway, there's also an online list of documentation and an online documentation for the package. The first thing to do is verify if effectively if the PyGeo has been loaded. From now on, PJ will be the brief form of PyGeo to call the package. So after loading the PyGeo package, an online help will be available in order to describe each of the methods and classes available within the PyGeo library. This is taken directly from the sources, but there is also online documentation for PyGeo on the PyPy archive, which can be consulted. I find this one. Well, anyway, not responding. Oh, this one. Finally, this is the documentation I meant with tutorial and other stuff. For what we are interested in this moment, what is significant is I'm looking for not installation, but probably the initial part of this tutorial. Oh, this one. I was looking for this drawing. Just to explain the data model present in PyGeo. First of all, as in rasterio, that gives you the possibility to access raster by using a simple open. In PyGeo, there's a basic class, a basic object that is used for the same purpose, which is called GIM. GIM is the main geospatial raster dataset object present in PyGeo. So you simply open a raster by calling this method. PyGim opens and gives you a lot of metadata, and it includes a series of methods to access bands, the multiple bands eventually present, and all other data connected to the geospatial dataset I just opened. So you can see, for instance, the number of column present in this image, but also information about, of course, its projection. So this is the conventional WKT representation of the spatial reference system. You already should know start from GDAL. Of course, GDAL is one of the many resources used in PyGeo to access information of the geospatial datasets. Of course, we already talked about the transform matrix concept. Anyway, this is simply the matrix used to transform the corner of the images to, and of course the grid of the image to the geographical coordinates expressed by the spatial reference system. In this case, we are simply looking a lat long, a lat long spatial reference system. Images are typically oriented north up, and with counting from row before columns, as in many cases, and also for the GDAL convention. This is the geotransform directly expressed. So as you see, it's very similar to something we already saw for Rasterio. It's almost the same concept. That's because GDAL has the geotransform concept abstraction, and so it is taken directly from GDAL from both Rasterio and PyGeo. Other information are about the number eventually present. Another concept introduced in PyGeo instead is plane. That's because in PyGeo, when you have a multi-band system, a multi-band dataset, each band could be a matrix, not necessarily a multi-dimensional matrix, not a v-dimensional matrix. So what is called a plane are simply the Z, the depth of the image, so the third dimension of the image. The other dimension of the image is used because typically a single band under the idea of PyGeo could be a time series. So each of these metrics could be labeled by, for instance, date or any other dimension that makes sense. Each band so can be a multidimensional matrix, and you can have multiple bands within each data set. And of course, dimension could be different, both for the X, Y, and plane dimensions. So in this case, we have just one plane. So this is a typical bidimensional matrix, bidimensional image, conventional one. One can open a second image, and one simple operation one can be done that can be done with those images is simply stack both them. In this case, you get now two bands for the same GEM object. Note that this is a general syntax used in PyGeo. That is, each object returns as methods that can be called by referencing directly the object. So in this case, we are stacking GPP to GEM, which is the initial object created. This one. So this is GEM. We are creating opening another data sets and then stack GPP to GEM by simply using this operation. So referencing the geometry stack band method of GEM to stack GPP. An alternative would be use instead a function to perform the same thing. So there's a PyJ geometry stack band. So now the name are the same, which is a function. This is not related to the GEM object, which can be used to stack together GEM and JPP. Those alternatives can be used both in PyGeo to perform all operations. So you can always use a single object you already opened or created and its method, or instead use some function taken from PyGeo as a whole class set. Again, the result in this case is exactly the same. So number of bands is 3. Why? Because we appended GPP to GEM, now appended again GPP to GEM. So we get 3 bands instead of 2. Another useful concept, this is taken from, I would say, essentially from the X-array package, which is another Python package. often used in the context of multidimensional array, is labeling the bands, so giving them names, and also labeling planes eventually. In this case, we gives band names ET and GPP, and the plane names for this we use simply the date associated to our data set in this case. And set dimension means we change the properties for the Gene object just to labeling the band names and the plane names. This is useful to reference later bands and planes by labels instead of numbers, which is a quite useful, helpful approach to understand what is going on. That's because if you use dates to label a layer, you probably will have it will have a better semantic in respect to using simple indexes. Of course, all these are quite simple operations because works only on the properties of GEM. And so we have now dimensions that are ET and GPP, and a single plane, which is numbered as 1. We can continue with some other operation. For instance, this is a way to crop bands. So starting from one of complete data sets and only and removing part of the information. So removing reducing the object to one single band and forget the other bands, and so on, also for eventually for planes. So this is a way to crop by name too, instead of number. So note that one can reference the bands and the planes by still index or by label. Of course, both gives the same result. That's because the properties gives you again the datetime for the plane labeling and the GPP for the band. Of course, multiplane means objects that are that could be possibly also interchanged. So if you have from start multiple single plane band, you can convert those bands to multiplane single bands. Doing something like this. In this case, we simply converted the bands to planes. So we have now a single band with the 2 planes that are exactly the same raster that we had as a separated bands. Oh, this is an example of composite with using an elementary reduced plane method. The idea is taking the data set, taking the band, which is composed by multiple planes, and perform atomic operation on each band by simply working on all its planes. So you can perform a single operation, in this case, compute the average, by simply reducing planes. So you are doing an operation that probably you know by something like Google Earth Engine, that is the map and reduce operation. In this case, we are reducing all plane to a single plane by computing the average for each pixel in a single operation. Note that that could eventually causes overflows in computation. Because probably some of those pixel contains not valid values, or overflowed, so the values overflowed while performing the average. And of course, PyGeo is also able to compute basic statistics such as mean, max, and mean, in this case, minus inf, due to the previous overflow. If you try to perform this operation, you are selecting only statistics for a filtered image. So you can use an elementary thresholding simply to transform the pixels that are under 0 to 0. That's because we know that the problem here was the presence of minus infinite in the image. That is probably the no data present in the image. So now we are simply filtering out all negative values and replacing them with 0. The result, of course, is that the minimum is this value, and the mean is this one, because we have no more an infinite. Note the minimum here was essentially minus infinite, and the operation, the mean, overflowed for that. Now it's all working instead, because we filtered out with a simple operation the wrong pixel. The reduced plane simply reduce the G-mean to the single plane that it has as a dimension. Other operation, I think that it's good, yeah. It is possible creating composites by providing a callback function. So in this case, we used a mean that is a predefined operator, but you can define your own operators. In this case, we are creating a getMax, which is a very simple example. This function will be used to perform exactly the same operation, that is the reducer. The reducing by simply using a custom callback function that perform operation on the matrix. So this is the definition of the function getMax return this operation. This is the supremum is the maximum for the whole matrix and plane present in the image. The geometry reduced plane is exactly the same operation done, but using getMax as a user function instead of mean. So you can pass both a function or the name, the label of an operator quite easily. The crop is something that can be done also to extract only one of the plane of the image. In this case, you will see that it works by using the label, but you can do the same also by index. So always label and index should work exactly the same way. And in this case, again, there's as you can do band to plane or plane to band again, and moving from one representation to another representation. Of course, within PyGeo, NumPy is the main sub-package used, and so all operation can be done that can be done within NumPy can also be done with GeoPy representation. First of all, you can see that GMP reference to the NumPy object present within the gem object. So every time you create a gem object, you already have the possibility to use NumPy because the plane and the raster are essentially loaded with the gem object. And you can see, of course, that the type is that of an ND array, that is the multidimensional array of NumPy. If you remember what I said the last time, remember that NumPy array are not built-in array of byte, are different type of object. And one can use the NumPy directly in order, for instance, use the sum function for pixels that are where the Gmax are minus than the average. Of course, you get 0 because I think that was the filtered image. So that's the result. Just to verify there are no pixels that are under the average, the mean of the gem object. Of course, you can reference also directly using gem the NumPy array by using simple indexes. So this is a case we have, of course, the choice of in this case the first 3 rows and columns starting from 0 for the single band of gem, or even you can do the same using negative indexes, which means the same 3 rows and columns, but starting from the end of the image. Yes, Giuseppe.
Yes, Francesco, when you convert it to the NumPy, a bit up gem.numpy, that one is a completely new object, so there is a kind of data replication, or
convert? No, it is directly referenced within the gem object. It is not a data replication. That's because under the hood, gem uses directly NumPy. That's not something like a data representation as gem and a data representation as NumPy. It's the same thing. I mean,
okay.
So we shouldn't try and use that in a way where, for example, we were assigning a NumPy version to a different object. It's just a different representation of the same thing.
yeah,
okay.
yeah.
Okay.
Yeah.
Well, good point, Giuseppe.
Yeah, because for massive data, we don't want to.
Yeah. Oh, that's one of the point of the as for stereo also in Pygeo. There's the possibility that you can use tiling. That's the right way to avoid to have extended memory footprint for your scripts, as it would explode due to the size of the images. So among the other properties, of course, gem has for each of the subset, you can get exactly, for instance, the bounding box. So in this case, we are interested in understanding what are, for the last 3 columnar rows of the image, what is the bounding box, and this is the way to express that in Pygeo. You get the bounding box directly as a property of this part. And this is, of course, the representation in as a simple built-in array for this 3x3 little matrix, right? With flow 32 as a representation. It's nothing special, but for, yes, right. That's simply a way to, because you can of course assign also in a matrix form matrices. So in this case, you are expressing a simple idea that this 3 by 3 matrix needs to be zeroed, and you did this just by applying this simple vector operation. So you are creating something like this just to see the difference. You see that if the 5 by 5 matrix that include that one show just the zeroed elements and all the rest. So that's just to understand that most of the operation that are conducted by PyJ or are vectorized. So you are effectively doing matrix arithmetics instead of scalar arithmetics. Another thing, this is quite common with also Rasterio has its own, if you remember, visualization methods, which are quite useful. In this case, you have the possibility, you see that the PLT is the plot in the initial load is the matplotlib. So in this case, PyGeo is using simply matplotlib to show exactly the same thing that in Rasterio is built in. Just to see something like this. Nothing special under those regards. It's simply the use of matplotlib to show basic images by taking in consideration the use of NumPy that is managed directly by Jim. So you are simply showing the image, referencing the NumPy reference for the PyGeo object. And so on for other, in this case, another easy thing to do is using, in this case, external operation like the medium filter available in the image, which is a sub package of SciPy, just to work on the NumPy part of the image. So all those operations that can be conducted on NumPy can be conducted on any GEM object by means of the reference to NumPy. Nothing special on this regards. And again, it is shown as a result by this is the median filter on the same image. Other interesting parts are, for instance, of the conversion of NumPy to GEM. So you can always use NumPy to transform, PyGeo to transform NumPy objects. This is the result of some operation conducted directly on NumPy in a GEM object. What is the advantage? The advantage is that GEM is always a geospatial object. NumPy results are not. So when you convert one into another, you get the possibility to write on disk, on storage, your data in a geospatial format instead of a simple numerical matrix. In this case, one has to simply using the PyGeo to create this mapping, which is a simple one. One has to use set projection and get projection just to dress your matrix with the right information, so the geotransform and the projection. Generally, when you do this, simply clone the geotransform and the projection taken from another object, which is your target reference, And so you can simply tag your results with the right information and write out the PyG result as a geospatial dataset. Oh, this is about calculating median filter. Nothing special. One other part I say is that also interesting is the possibility to mix together X-array and GIM. X-array is another package is quite common in use for numerical analysis because X-array is a package that mix together labeling and multidimensional dataset. So sort of, I would say, data frame as in pandas word or in the R word, where the basic objects are matrices or stack of matrices, and so you can mix together values and multiple rasters all together. You should think, I don't know if you know the well-known format netcdf, but X-array is essentially the representation in memory of a netcdf file. netcdf file is a collection of raster data mixed together, other information that could be labels or values too, scalar values, all together represent a dataset where you have not only a simple raster object, but a collection, a full coverage with additional information, which could be parameter to use to perform a specific operation. This kind of format is quite commonly used in geospatial analysis, specifically for remote sensing, where each satellite or each map is dressed with additional auxiliary information, big quantity of auxiliary information that needs to be provided along with the images in order to perform your analysis. So X-array is simply, to let me say in a simple manner, it's a simple way to represent in memory with Python this kind of data model and work with them. One advantage of using PyGeo is the possibility to cross-reference X-array objects with PyGeo. So this is really analogous to the NumPy, and again, you have the possibility to refer projection and geotransformation. In this case, the geotransform and the projection were already labeled previously by GIM, and so you are using this to present the same object. So you should think to GIM as a sort of container where you can reference, and of course, when you use X-array, objects are allocated. When you do not refer to X-array, I mean the X-array reference within the PyGeo, you are not allocating nothing in metal. So you allocate stuff only when you use effectively use those stuff from Pi or X-array. Never they are loaded at load time. They are created on fly when you are referencing all of these objects. And so again, there's the possibility to use labels to refer data, X-array data. Note that it is again an AD array. That's because X-array under the hood use NumPy, but add layers about with that. Again, one can compute the median in the case of X-array. Here is commented out because it can take several times to run. by rolling pixel by pixel the median on the X-ray object and then visualize the final result. Of course, GeoLib is PyGeo is also can work with vectors, and of course work with data frame taken from pandas, and work to extract, for instance, using, as in this case, can compute zonal statistics starting from vector information. Okay, this completes just the very brief introduction to PyGeo. I think that Giuseppe will present. Yeah, Giuseppe, you have a question?
Yes, in the same line of the previous question.
Yeah.
You mentioned that the gym.npy is not replicating the data.
Yeah.
But as a user, how I can understand this concept? I mean, how I can see that is not replicated data. If there is any tricks that I can show that one is the new object, but just an interpretation of the same object?
The objects are loaded when they are referenced the first time. So in general, if you do not use X-ray representation, there would be no replication of the stuff. In general, NumPy needs to be expressly addressed to replicate stuff, else old stuff is done in place. And so when you change something, as in the case of this operation here, where I change this one, okay, you are working directly on this data. So there's not a copy of the data to create. So when you alter the gym subset, you are altering effectively the gym subset within the image, not on the storage, but in memory. So from now on, that should be taken in consideration because you change the data and you have not a copy of the data. So in general, all changes are done in place. I hope to answer your question.
Yeah, of course. Yeah, thank you.
Memory footprint is something to take in consideration always, but fortunately, Python, at least for what it is about the advanced packages, has less memory footprint than, for instance, MATLAB solutions. That's for the proprietary work, where instead the language tend to copy matrices every time you pass them on functions and every time you return them from functions. So the memory footprint is less important than in other languages like that. But anyway, it's something that you have to take in consideration. That's the reason to use tiling, for instance. And so do not manipulate the whole length image altogether. So as I said, in the next lessons, I think you will show some classification down using PyGeo, right?
Yeah, there is a class running from Peter from last year. I'm going to add into the syllabus. Actually, I already added, but previous day, but I'm going to replicate again.
Okay.
Use this concept of basic, and then make a classification of an image using forest. But then it's the same concept. You can use any other kind of modeling. Okay, so this kind of all this kind of PyGeo implementation are very useful in the moment that you want to enter inside a bit more in the processing of the image. We make several GDAL and PK tools were doing kind of pre-processing, and now that you are inside the PyGeo, you can do all heavy processing with image classification, subpixel analysis, time series analysis, all this kind of So I really suggest to go deep in the use of PyGeo for this this kind of analysis. Everything is kept in memory, so they will be quite fast, especially if there are several, let's say, steps of time series, for example, to go through your kind of computation. Okay.
Okay.
Any other question in this regard to PyGeo? Or
And even eventually rasterio uses, because we are moving to completely different arguments, so probably it's better to, I don't know, maybe we could anticipate a pause eventually.
Yeah.
That's because we are simply switching completely the topic. So
Yeah.
probably it's the best way, the best moment to do that.
Do anyone other question concerning the PyGeo? If you are already thinking something, and
Julia?
Yes, I was thinking about once again the conversion of NumPy, the use of Gym NumPy, because when if I understood correctly, PyGeo can handle both bands and planes, so time series
Yeah.
for band. But when I convert, let's say, in NumPy, I lose this, or it's just a sequence of everything. So maybe the question can be, how can I distinguish between band and plane when I convert in with NumPy?
Oh, that's something that is done every time you work on NumPy, of course. The press when you work with planes, you are completely within NumPy, PyGeo. So when you switch from that representation, you have to do that explicitly, because the NumPy representation is a more simple object, simpler object than so not multiplane. Is something more elementary. So you have to switch from one to another, and take in consideration that when you work on your data model, of course. What is important is this is the same approach used also in X-ray, where you have to switch from the data model using X-ray, which is more expressive, to the NumPy, but you do that only when you can find a function that is useful enough for your purpose within the X-ray or the GeoPy model. And you have to use, for instance, a third-party function to work on only a pure NumPy object. So you have to use that and make this move. That's the reason to have this Gym to MP to Gym and conversion from band and planes. That's what was the basic reason.
Okay, great, thank you.
And Leonardo?
Yes, if I have some data in netcdf format, and I want to do zonal statistics, which is the best way? Is best to use X-array or some netcdf
Package, you mean? That's a good question, and it always depends on what you are going to do. That's because netcdf as a basis system has its pro and cons. So if you can do what you're interested in, only staying in netcdf, it's okay. But if you need something more expressive, probably it's better using X-array. X-array gives you more layer of representation, more functions. So probably you will not use directly netcdf. Also, X-array is parallelized under some regards, so it could be useful. It depends on the context of work, and even also the eventual infrastructure you're using. That's because as a basis, both density of physics array have their own vectorizing approach to work on big data sets, and you have to explore one or the other. That's not the perfect. So, as always, the right answer, it depends.
Okay, thank you.
Any other question?
Yeah, any other question?
I have a question. So I'm now using a Rasterio model time, and then yeah, I wonder when should I maybe use PyGeo, because I see some things Rasterio can also do. Yeah, so yeah, what do you suggest? Like when should I use what?
It's Rasterio is quite it's now stabilized enough. Stabilized, I mean that the development cycle has been intensive in the past years. Now it's quite more stable on their main aspects. Something what had to change during the time should already be changed at the time in 2024, I say. They are both good product. You have probably maybe to consider that both product under the hood as small teams to work on the packages, and so you probably can use them alternatively. It depends. If you know both them, you probably will be able to decide when it's better to use one or the other. At this stage, supporting PyGeo for deployment, for instance, so to deploy or to give software to other people could be more complex, because the deployment workflow is not so linear as you see. But this is the current stage. It is interesting under many other point of view. So it depends on your targets. If you are going to experiment for your own workflow, it's a completely different respect with giving your software to other people, and they have to work on another platform. When you have problems, supporting them could be a problem or not. It depends. Definitely, when there's something that is quite in fast development cycle, generally you cannot give your laptop to third people to have something working. That's the point of view. So you have to have something that can be installed straightforward, and probably at this stage, Rasterio is the immediate answer to this thing. If you can take your time to do things, probably PyGeo could be a good answer.
Yeah, thanks. Yeah, I have to share the code to others, so I think that Rasterio is a better way. Yeah. Thanks.
Francesco, in terms of speed, what do you think is better?
Well, that's as you've seen in the last lessons. The speed is something which you have to research during the development cycle, because it's not always evident and simple. Understand how you should write properly the thing, because it depends on what you are doing under the hood. So both them use NumPy, and in some way also X-arrays, NumPy, so on. So you have to cope with those packages. It's not always simple. You could have bad performances, for instance, and need to find the reason for that. And that could take time, because you have to understand how the things are done through NumPy, for instance, and find an explanation for the bad performances. It's not always evident. You can stay for a couple of days on a couple of row of code because you have to solve a performance issue.
Yeah, thank you. Okay, any other line or a question in this line? Okay, so we may go to a break. We
Yeah.
come back at 35, 20 minutes.
Okay. Okay, absolutely, it's visible now. So now an argument completely different from some time never seen in the past edition of the work on the course. I think last year we talked briefly about that. The rationale about presenting a few notions of geospatial SQL is that, in my opinion, this is a required background that anyone interested in spatial geoprocessing should have, at least at level basic background. For sure, a lot of advanced geoprocessing can be conducted by using those tools, and even in many cases, when you have to manage massive quantities of data, I mean, millions or billions of rows of information, all with geospatial localization, it is not possible to avoid using this kind of tools and languages. So I think that anyone really interested in geoprocessing should have at least basic notions about SQL. So structured query languages, familiar languages that was born in the 70s, so it could be considered part of what is called legacy software, but it is intensively used in many domains of applications, and even the geospatial context is not an exception to that rule. What is used in this tools and language is what is called a relational model for structured data. If you think to the concept of data frame in pandas or in R, or even in other data representation in other languages, for instance, you think to at very general level in terms of tables with columns or attributes. So the relational model is something that is directly linked to this aspect, to this thing. A relational data model is a representation in terms of multiple tables that are in some way connected among them. So with relationship among tables, among their attributes and rows, that can express a complex domain. Think to data frame as a collection of dates, scalar values, strings, whatever you like, times, and so on. As a general concept. So SQL is simply the generalization of this representation, and above all is an implementation of a language that is able to describe this set of tables and relations, express queries on those collections, change those collections, and create massive procedures to manipulate and to query those data in the most complicated way you can think to. At the basic of the relational model, there's a mathematical abstraction that is called the so-called relational algebra. Think to theory of sets simply, and so all operations you can conduct on tables and relations can be expressed in terms of unions, intersection, difference, includes, negations, and other basic operators of theory of sets, of the mathematical theory of sets. While the SQL was born as a pure declarative language, today it also includes a lot of control flow instruction and also procedures and many others. The current standard by ANSI is also extended by specific implementation to express a lot of different operators and selections on the data. So an example of this query, of this instructions is something like this. This is typically a classic SQL query. In this case, this is a manipulation, that is an update to one of those tables here expressed. You express something in a very simple and expressive way by using an update clause. So you say you are, in this case, saying that you need to update the table countries by set one of its columns called population to a new expression that is sum 1 to the current value of the population column, where the name of, so the column was name is name, where the name has an expression that is like USA. So in this query, you are simply expressing a statement to change the content of a table in a single expressive way. You should think that all operation done on SQL models, on relational data models, is expressed exactly in the same way. Of course, I have no ambition to present to you the whole SQL language, because it would be quite impossible. But we will see a few simple application for the data we are working on, just to understand the potentialities of these languages and the current implementation for our application in the data science and the geospatial domain. But for the ANSI standard for SQL, also in 1990s, the so-called Open Geospatial Consortium, which is a committee essentially, has implemented also some extension for SQL that is currently called the proper standard for expressing in SQL geospatial queries. So when your part of your attributes are can be expressed as in terms of geospatial location, so you are for sure using some kind of spatial query that extends in some way the basis of the language. Now, in the real world, there are a lot of different implementations, so different dialects of the SQL, and main system that implements a type of relational model and of the SQL language. Well-known database are Postgres, and specifically PostGIS for geospatial world, but also MySQL, MariaDB, Oracle, Ingress, Microsoft SQL, Sybase, and also SQLite, Spatialite, and GeoPackage are also well-known names in the SQL world and also for the geospatial. All those DBMS includes a geospatial extension. So you can use geospatial extensions that are generally OGC compliant with any of those systems. Those in bold font are typically what we use in the fourth word for geospatial queries. That is PostGIS and Spatialite. GeoPackage is also interesting stuff because it is considered today probably the most spread exchange format for the geospatial information. It is not a spatial SQL as such. It does not include, for instance, geoprocessing capabilities. But its standard is well established. It's an ANSI standard too. Those tools can include or not support for what is generally called data cubes and even rasters. But the OGC standard per se do not deal with raster data. It only deals with vector data. So with object like point, lines, line strings, polygons, multi-polygons, and so on. Often in the real world, there are at least two different approaches when you have to manage with rasters data or data cube. That is embedding the rasters within the database or not. So instead using an external object storage and collecting in the database, in the SQL database, only the metadata, the meta information of the raster data. And so you use that just to dive into the raster data and take the raster model of the raster dataset that when you need from some sort of storage. That is, for instance, the approach used by essentially all agencies when they provide you with maps or satellite images or any other thing, because generally the raster objects are quite huge, and so they are stored in a specialized data storage that is apart and instead with the database that provides instead metadata of them. Now we will concentrate on a simple, you can use it very simply, a simple geospatial database. It's a Spatialite, which is a portable relational geodatabase. Its characteristics are it is a single library solution. So just in order to use Spatialite, you only need to install a library and create a single file, which is the contents of the whole database. You will use some programs, some tools, some command line tools, or any other third-party solution. For instance, also QGIS is able to open Spatialite files and perform your geospatial queries by using simply a simple basic library. It is also multi-threaded, so it can be used by multiple processes at the same time. The only constraint is that you need to have one single process to write in the database, but a lot of different processes can at the same time read the database. So the lock is really limited. It's a perfect solution when you have, as in many cases, the right ones read many pattern to approach your data. It is fully OGC compliant. It's very fast and compact. There's no need of a server as in the other cases. You do not need a central server, huge server to maintain your data and a service listening on some TCP port to answer to your question, to your queries, and aiming to maintain this kind of infrastructure. It is very scalable, even for tons of gigabytes of data. Just for instance, we use internally at work for most of our data a single specialized database with almost 50 gigabytes of information in, and is perfectly usable as such. You have to consult both specialized documentation and SQLite documentation in order to use this product. This is the documentation available as in SQLite. This documents the general SQL language implemented by Specialite. And this is instead the documentation for the functions available for the Geospatial part of Specialite. So when you write your own queries, generally you have to resort to work with both documentations. That's because Specialite is essentially an extension of a basis product that is SQLite. So it works as a Geospatial layer over the SQLite. SQLite is an older product. It is in production since, I think, the very start of this millennium. It started as SQLite in 2000, at the beginning of the 2000, and now it has almost 25 years of age. Specialite is more recent, but it is also quite old now product. Well, quite stable. I think it is available since maybe 10 years or more. For the installation, one has just to install this this product. That is this is the module that implements the Specialite part for SQLite 3. This is a tool, a set of tool, command line tool for working on any Specialite database. And there's also a simple UI, Specialite UI. It can be used to read information about Specialite database. You can also use QGIS, for consulting the Specialite database. Of course, the first thing to do when you work with when you want to work with Specialite staff is verifying that there is a support for SQLite. This is the command line to verify that Specialite is available. In this case, it is. There's also a more tiny layer that is called rasterlite, which gives you the support for embedding also raster within a sort of Specialite database. Of course, there's also a package for Python, so you can simply install Specialite. It is already installed here, again within the virtual environment. You can simply ignore the fact that it's a very starting initial version. That's because this Specialite package does very few things. That is loading the SQLite support and then loading the Specialite external extension model. So something very simple, nothing special. It's a simple brief mode to perform this operation. Within a Python package, you can simply import Specialite, and then doing very simple operation, we will see some typical pattern of use within a Python script for this product. In this case, I'm simply executing a simple query that is get me the Specialite version currently working. This will return a list of information in general. In this case, it returns just one row that includes the version number, that is 501. And you can also perform instead command line operation by using, for instance, Spatialite the command line tool. In this case, Spatialite new.db is the command to use, and what follows the name of the database is simply .tables. In this case, it gives this output. It gives you an header where it explains all the extensions that are available when you load Spatialite on this box, and gives you also information about all the libraries used under the hood by Spatialite, and show you the full system of an empty database of for Spatialite. This is simply something that is created on fly when you create new DB. So when you, as asked after this, if you make typos in the connector, you are simply assuming that you are going to create a new Spatialite database instead of getting your data. So you should avoid to use the wrong name when you are interested in working on an existing database, because you could simply open the wrong empty one and being worried to have lost your data, which is not. You have simply to use the right name, because if the database does not exist, it will create one. Now we can take our times to have a look to the command line object, Spatialite, the command line tool. So this is a sort of Python-like interpreter where you can give your information, your commands that includes a series of dot commands that works on the whole system of tables and permit you to doing multiple different operation on the database. But in general, what you can do is simply writing a query like this one. What I tried before is simply email the table's name. Of course, Spatialite is a system that with an extension that creates a layer for geospatial analysis over the basic empty system of tables of SQLite. So it is adding a lot of different tables for a series of purposes. You can see, for instance, that Spatialite is a topological database. So it's not like it's not something like a shapefile. Shapefile is not topological, so there is no information about cross among vector, among lines and polygons. It's a very incomplete implementation of a vector data model. There are a lot of different information, such as stuff dedicated to PMS services, stuff dedicated to implementing views, that is specific view of your data for a specific use. There are important information about the spatial reference and many other information that are embedded in your own database. So when you reference, as in the case of NewDB that I created in the previous step, I'm simply showing you exactly the same information, but you know that an entity database, Spatialite database, is something like this. So it has already something here in that includes the tables, the system table, that are created on fly. Okay. Spatial light theory is a very simple vision of the schema of your database. You can open, of course, or connect in terms of SQLite your own database and see what is within the database. It is also able to connect external service-based, such as PostgreSQL database. And so it is in general a quite general client, which is usable for many different users. You can see at this level multiple indexes and information about your topologies and vector. This is still an empty one database. Now we will see how we can populate a database in very simple ways and try to understand what we are going to do with this kind of system. Yes, some key aspect of SQLite concerning the concurrent accesses, the so-called transaction cache. So there are part of the commands in SQL and so in this part and Spatial Light that are dedicated to scale up the database so that it can manage in most effective and fast way the data. So those directives are generally used to introduce tricks and to fastify your access to the data, but it is of course something that you will want to explore when you have to manage big data and big number of data. Think that a big system of table is not a table of hundreds or thousands of rows. That's a little one. So you have to think to millions of rows and thousands of tables in order to think to a very complicated, very complex system of tables, database, that needs to be tuned in order to maximize the performances. In general, this is not requested for most of the cases. So let's try with some real data. You already have the experience, I think, with a GeoPackage, because in a previous, in the usual 3.8 application, you already have this database among geodata vectors. Maybe you had a look to those data. Maybe Giuseppe can be can give details about that. I think so. Yeah.
You could have under the 3.8 folder that has been downloaded a few weeks. You should over there, right.
So this is a very simple file. It is an OGC GeoPackage file. So this is again, a GeoPackage is a special format of SQLite. So in some way, it is very similar to this one, which is again the newly based Spatial Light we created before, which is again a SQLite database. Nothing different. What is different is the system of the set of system tables used, and the fact that when you work with Spatial Light, you are able to perform geoprocessing. GeoPackage is a very limited implementation instead, which is again based on SQLite, but it is only thought to distribute data, not for geoprocessing, but only to work for give your data to other people. They have to import the data within their own processing system and then use that processing system to work on the data. So the purposes are quite different in the two cases. Instead, we will see in a few that you can perform quite interesting processings on the data just working with the spatial light. So just to import, we will first of all see how this GeoPackage is done. So you can see that it's of course geolocated. There's an extent and there's a WJS84 reference system. It gives you also information about what is the feature ID. The feature ID is the key used to identify each feature present in the GeoPackage, or even we will see in a few also in a table of the spatial light. The feature ID means that we have in this database an ID and the height of the tree. The ID is the same as in the FID column. And there's also a column that expresses the geometry. We will understand soon what is the meaning of this concept. Indeed, if I try to, by simple OGR, have a look to the information here present, we are just looking to the first 5 features present here. This is a simple representation of the content of the database for its first 5 rows. So each feature is a point. You see that the geometry is a WKT representation. Giuseppe, did you talk about the WKT representation for features, maybe in the past lessons?
No, it's better if you say something, yeah.
Okay, WKT is also cited here. That's because this representation, this one, is even a WKT representation. It's a representation of the spatial reference system of this system. So a way to, a standard way to express the projection used, in this case, it is not projected, but it's only a specific case. You are expressing the datum, the type of projection. In this case, it is a not projected world geodetic system 84 representation. So the WKT is the acronym for well-known text representation. It's simply a way to represent in text format a piece of information. In this case, that of a spatial reference system. But you can think to the same thing when you represent in this case a point. This is the WKT representation of a coordinate, so of a geolocation. Point followed by parentheses, where the first coordinate is that of a longitude, the second coordinate is that of a latitude. Of course, if you have added a Z point, a point with that, we will see 3 coordinates. The third one is the altitude of the point. You can also have a 4 coordinate, which is time. So in OGC standard, this is the so-called well-known text representation of a point coordinate. Simply point followed by point, or 0.3 or 0.4, followed by 2, 3, or 4 coordinates in a standard way. Then for each point, you see there's an ID that identifies the number of this coordinate. Think to that as the number of the row in the table, and the height of the tree in meters. Okay, so you should think that each of this table, each row of this table has 3 or 4 information better. The first is the so-called OGR ID, which is casually also coincident with the ID column, then the 8 column, and then the coordinate point. The coordinate is a geometrical column that is included with the data. So you are expressing the information here present. Now we are transforming this package, this geo package, into a typical representation that is a shapefile for vector data by using OGR to OGR. It will take a few time because there are a lot of different coordinates, I think 1 million or more. We will see also the time required to manage this conversion. Why I'm moving from GeoPackage to Esri shapefile? Just because I'm going to import as a spatial light database this information, and spatial light gives me a very simple procedure to do this thing, that is using the .load shape format, which is able to load any shapefile within the database. So it took 48 seconds on my machine, and now we can simply load this information. We will see in a few that it will complete. So it is giving evidence to to what it's going to do. It is creating a table named 8 that includes a primary key that is equivalent to the feature ID we already saw in the file, followed by the ID and 8 that are exactly the same information here, and also is adding a geometry. Note that this is the number of rows now present in the shape taken from the shapefile and passed to the spatial light database. So it is also including a geometry column that is the type point with 2 dimensions, and then it is registering all the required column within the file. This is also give me the occasion to I think there's a part about transactions here or there or after with an image. I also here, yeah. An important thing when you work on spatial light data with spatial light in a programmatic way is taking in consideration that the most efficient way to inject new data into the database is opening a so-called transaction. This is a sort of start and end of operation on the database. This is something that the load shape is already doing by its own. So you see here begin and commit. So this is the fastest way to load stuff, inject new stuff in a database, in a spatial light database, or in general in SQLite. But for this after begin and before commit, we are doing an important operation. Then we are simply giving evidence to this, saying to the library of spatial light that from now on we are going to do something that locks the database for use. This way, it will register this operation, but also this one, because after the initial transaction it is started also another transaction here, which is not visible at all, just before inserting the first row and after inserting the last row. So what is interesting is that when you begin a transaction, at the end of your work, you can do two different operations. You can commit or you can roll back. So in a certain sense, when you commit the changes, you are physically writing the data in the SpatialLite database. If not, you will roll back so that all your changes will be discarded, and so the SpatialLite will be again, of course, empty instead of being populated on your injected data. So this has two different purposes. One is to fastify your operation with a single I/O operation, and the second, you have the possibility to perform operation in atomic way. So if your work is composed of two steps, A and B, you have the possibility to perform A and B and then commit the changes. Or instead, you could perform the step A, discover during the step B that something is anomalous, something is wrong, and then roll back the whole operation, and you take the SpatialLite database consistent because both A and B will be discarded. That's the sense of a transaction. That's because when you make changes, you do generate changes step by step. So a transaction is useful to avoid to leave your database only partially updated, which is the wrong way to, which would be the wrong way to manage your data injection. That's the sense of using a transaction as in this case. And so it has also the purpose of being very fast in its operation. So now we have loaded our information. Note that we after the OGR to OGR, the effective the real layer shape is called new layer dot shape within the AOXYA let's select directory. After that, we can simply use the SpatialLite database to perform our first simple simple processing. So, for instance, here we are extracting information about the heights of the present in the file. We are interested in understanding what is the mean height, the mean, the average height, the maximum, and possibly also this one. This is the standard deviation of the height. It is instantaneous on 1 million of rows. If you try to do this operation on the initial, not the geo package, but think to what you have to do with a regular CSV file, for instance. You should write a script to load each row, each 1.2 million rows, taking into consideration each of the interesting fields, and compute average and so on within the your code. Probably the I/O phases would be quite long because 1 million rows is not so easy to load from a CSV file. It takes some time. This can be done very simply by using instead SpatialLite common functions. And this is also the occasion to show you this one. Why I use this formula to compute the standard average, the standard deviation, sorry. Simply because in the standard deviation is not one common function available within the SQLite library. So you have to use a different way to compute the standard deviation. And why it is not? Because of course, this is a very basic library that provides essential function. Not essential function are not provided. And that's the reason is, of course, that standard deviation can be found by using a simple formula. There's no purpose in including also a standard deviation formula with a standard deviation, function within the SQLite implementation. This is, of course, not true for all databases. So there's a reason to have directs. Spatialite and SQLite are implementation that are provided in order to be compact, fast, and simple. If you need more advanced functions, you have two different strategies. You can provide your own add-on extension. It's written in some language, for instance, in C or C++, to perform on a not provided function. Or you can use another DBMS, more expressive. It could be PostGIS that provides more functions for both manipulating the attributes or even the geospatial part. Now, let's go on with other information about, so I already talked about the transactions, but now we will see how this approach can be useful. What is missing in general in managing attributes and geometries? Think to the CSV file example. If you are interested, for instance, in selected only by geometries some information taken from this huge collection of rows, this is something that probably cannot be done in a simple way by a program, because you need to select with advanced geoprocessing capability points from the table, and possibly also mixing together with the selection done on the attributes and so on. All those kind of advanced geoprocessing are difficult to be performed by using a single tool or a single library within without using a geospatial engine like the Spatialite and the SQLite. So let's see some very simple example like this one. We are taking this table that is coping. I think that this table is should be available for all of us because it's the result of extracting from the rasters point by point the value in each of the 1.2 millions of rows of coordinates. For each raster, this will be contained. For each geolocation, it maintains the values of the raster or multiple rasters in the same geolocation. So now I'm copying this into file CSV. Just a trick, because OGR next step is to open by OGR info this CSV file, and OGR info does not like dealing with file with extension txt. It prefers a more expressive extension that is CSV. If you try to use the same command on the txt file, you will get an error. Instead, we can do this and see that a CSV is one of the legal vector file for OGR info. This is the content. Again, it's very similar to the previous one, but we add something like, again, the feature count is this number with, again, there's no information, of course, about the spatial reference system, but we know that the coordinates are those in WJS84 we used before. And we have all the fields included here that are taken from each one from the raster provided in the dataset. So we have all those fields. So now we can simply, by OGR again, import this vector file directly into spatial, spatial light by using OGR to OGR instead of the load shape from spatial light. The syntax to use is simply this one. You have to specify that the format of output is an SQLite with a dialect, which is a spatial light. Here we're asking that this field name I used and clean adapt for as a name for the field in the table. So for the column in the table used in the spatial light. That's because often there are a few limitations about the syntax of the column. So it's always a good idea to force the laundry, that is translating the name of the columns in something that is legal for as a name for column within a table in SQL. That's the idea of this option. And we are also suggesting what are the names used to be used for the coordinates in input. So we are saying that X and Y are longitude and latitude. And what else? We are passing the output file and the input file, which is the CSV. It takes some time. Now we will perform some simple operation here, just to have a notion about what is it for real geoprocessing for spatial light, by doing exactly what I suggested. That is, starting with selecting by geometry. Yes, Giuseppe.
Yeah, Francesco, why is so fast? Because there is an indexing, or?
Yeah, that's within the spatial light there is a so-called two type of index. One in system of index is about the attributes. So there are all attributes are indexed. The other part, the other important part is that the geospatial attributes, that is the geospatial coordinates, are also indexed in geometrical way. Within the database, there's an R tree that perform fastly research based on geolocation. That's the reason to have fast search. So it took 1 minute and 31. Now we can perform a lot of different operation. This is again an OGR info about the new object that is a spatial light. That this is a spatial geometry with point. Geometry column is a geometry. Now we are simply saying, okay, give me just the first 5 objects. I'm using ID in this case. Note that the ID is a string. So I'm interested in giving an expression with an arithmetic expression with a search about the first 5 elements. So I'm casting to integer the ID, which is a string. Note that all fields here are strings, but you can easily convert on fly or even use the default capabilities of spatial light to convert from string to another scalar value. We will see in a few. So we'll see that there's an extent already completed. These are the geometry. I'm extracting exactly the number of the first 5 features here. Again, you see there's a point. There are the information here, just a few. But I can do better because I can, for instance, okay. You can see that you can do exactly the same thing by selecting the OGC feed, which is and using OGR info. I'm selecting by OGC feed the first 5 item, the first 5 feature in the split in the spatial light database, and get the same output. But the most important thing is instead, for instance, computing an average on all the elements for one of the field, QC A1, for all the elements in the table, for instance. And you can do this with a result 1.2 million of elements, or rows. And you can do the same for the first 5 features. And so you get exactly the first one, the first 5 features. It was probably the repetition of the yes. If you are interested in making some computation on limited part of the database, you can use the so-called ST functions, which is the extension of spatial light for SQLite. Here I'm going to ask him to give exactly the average, the number of records, and the average on QCAI field from the table, where there's an intersection between the geometry field of the row, that is the point, and a buffer of size 1 degree here around a point, which I'm giving it as a well-known text, this one, 0.649. This is the WKT representation of my point. So I'm converting the point in WKT in a proper geometry field. So I'm creating a buffer around this point of degree 1, and I'm using 100 to express, for instance, the kind of approximation I'm going to use. By default, it uses to draw a polygon around as a buffer. So it is creating a polygon with 30 segments. Instead, I'm more interested in augmenting this number from 30 to, for instance, 100. And so I can now have this new information. So it is going to select by geometry the average. It's none because probably the point is wrong. No, it's not fair. It's not finished. Sorry. Okay, that's one. So we got the number of points, that is 200,000 almost, and this is the average on those points. I can do better. I can, for instance, get the same result in that via spatial light in tabular form, because it's much more easy to read. So I can do this by OGR info, but I can also do this also by using directly spatial light. And that's exactly the same result, even probably more fast. Now, this is left as an exercise for you. Something that could be interesting is instead of providing a point, just trying to do the same operation and computing the average, mean, and max of every field in the table for all the points in a buffer of 1 degree around the center of the data extension, which is could be more interesting. So, what is the trick in this case? You have to find, first of all, the bounding box, and then find its centroid. How you can perform this operation? For sure, not by code. For sure, you need to use one of the ST function. It is suggested here. Find the layer extent, and then find its centroid. So, one should find this information. For instance, going here, SQL function for spatial line, and find, for instance, extent. We say layer extent. Get layer extent. Oh, there's a function. So there's a function to have, starting from a table, its layer extent. So the table is the content with a single centroid, a single geometry, probably. You can you can find the layer extent, and then you need also to find the centroid. Oh yeah, there's a centroid function, or better, ST centroid function that is returns a point. So probably if I try something like sorry, just shift that. Suggestions. How can I find the centroid? As this centroid. And that's sure. Then I have to specify ideas. You're lost. I already suggested that.
Like the centroid of the whole image?
The whole, yes.
Okay.
So something like this. Extend. Get layer extend. Note the get layer extend. So get layer extend is requires table, which should be a string. The other options, the other parameters are optional because there's the bracket. And returns a geometry. And we see that centroid uses geometries as an argument. So nothing more than this one. String, the name of the table. The name of the table we use is this one. And you generally should complete the query with a semicolon. Um, be completed. Let's try with this. Get layer extent. There's probably something wrong here. Let's see, sir. If
Be a semicolon in the end.
not sure. No, it's not the issue. Let's see from the terminal. It's more simple. Yeah, okay. First of all, we have to okay, without this. And the silent, it's probably will be avoided. So let's see. This is return a geometry, so it's better to write something like as text. That should return a WKT for the geometry. Okay, this is the geometry in WKT format. Oh, right. That's stupid. That's a stupid error, because one has to connect the mind when writing something. ST centroid returns a geometry, so you can't see the geometry because it is not something that you can see as a text. And okay. There's some error here in the writing. This was the right thing. Select ST as text. And this is point. I don't know why in the cell is not able to see that. Anyway, this is the result correctly. So we only need to repeat the operation exactly the same before, but instead of using this object that is stgeom from text, one simply can replace ST centroid get layer extent instead of this one, and then compute average and so on. That's just for it's an easy example, a very easy example to perform geoprocessing functions, but for complication due to the cell constraints in the notebook. Okay, now just very few words about how you could write similar operation within a programming a standard program. Basically, in a Python program, there's nothing more than what we already saw. You have to connect the spatialized database. This is the opening of the DB. Then in Spatialite, there's the concept of cursor. We will explain in a few. You are simply executing using a cursor the required query you are interested in. So in this case, simply I added this one. Sorry. This is the result, which is a special type cursor. Cursor is a class, so it is a series of methods. One of them is fetch one. So give me the first one of the result of this select, something like this. So this is the return of asking for all fields taken from our table. Note that at the end we have all the fields we already know. This is the number one, of course. At the end you see this one. Well, this is simply the representation of the geometry in binary format, something you are not interested at all. So it's better writing probably something like this. So taking some fields, then represent the geometry as a text, and you get exactly what you are interested in. And you can also ask for the longitude or the latitude, and even with instead of the text format WKT, it's exactly the same. But you can also do something this. So get all the results, 1.2 million of rows. Reloaded 1.2 million of rows, but of course we see just a few of them. And not something to remember is that cursor are not idempotent. What's the meaning? What do you expect now if I repeat the fetch all? Idempotent is, I hope, is clear for all. It's a mathematical expression. Huh? You can't repeat and get the same result. What is the result of this operation? You are fetching all again on the same result. Guess? Anyone is able to guess?
It's appended?
Not appended. It is again, ls again is another variable. What's the result? You can't repeat. So, well, mastery, solved.
Random stuff.
It's wrong. It's wrong. It's simply empty. You can't repeat the query. You have to re-execute the query, because when you get a cursor, the cursor is in terms of Python is a comprehension. So you have to follow from the one to the second to the third. If you get all the results and you pass to a variable, now the cursor is empty because there's no more data to get. They are all passed to the previous variable, so you can't use again the same cursor. You have to re-execute another query and get new results. So what is the correct thing to do now if you are interested in doing exactly the same thing? I have to repeat. So I have to repeat this one. Hold on. I have to repeat execute and get again results. So this is the mechanism to use when you are interested in using SQL. That's true for spatial light, but also it's also true for to repeat you have to use exactly the same approach when you use any SQL implementation. So the cursor are not idempotent. You have idempotent. You have to repeat the queries, get results, and then repeat again if you need more results, different results. So in this case, I'm using, for instance, limiting table, fortunately, to the first 5 elements and fetch all them. And these are the first 5 elements. something more manageable by using a notebook. Trust me, they are fine. Another little details is that you can instead of returning a simple list, you can also use the so-called row factory to get more readable results, that is dictionaries, by using this system. This system, you communicate to the DB that we are going to use a row factory. This is the trick to use. Then redo the fetch for all selector for all the whole table, and then you can see that after that you have notion of the name of the field within the table instead of simply a sequence of rows. And then you can at the same time see what is row 1, that is the first element of GC FID, but you can also use the label to access exactly the same field. So much more semantically significant in respect with all the rest. So any script will do exactly this kind of, you will use this kind of pattern. You start execute a SQL sentence, a SQL query, then get results, and you get the portion of the result you are interested in, one by one, or any number by any number, process, and they'll go away and prosecute with other operation. So you can populate your internal tables. You can use geospatial processing and geospatial queries to perform operation on the whole data sets at geometrical and attribute level and get final results in a smart way. So most of the spirit of the thing is that you have to pass to the SQL engine most of the analysis capabilities on the data, because you have to extract the synthetic, the synthetic way what you are interested in, and then your script does nothing but for collecting final results by geoprocessing, starting from the whole collection of data. This is exactly the pattern used in many cases by systems that have to deal with a lot of quantities of data with billions and billions and tons of data of this type. Of course, you can use the same approach to work on all type of vector data with multiple tables and constraints among them and so on to extract information. The only part that is taken apart is, of course, interaction with the raster parts. But as I said, there are two ways of working. In this case, you can use an SQL engine to manage the vector and extract meta information for the rasters, and then use the by rasterio and so on to work on the raster for the points you are interested in, for polygons and extracting other parts. Or you can use a more advanced engine that also includes raster management. And so you have to use the capabilities of that engine and forget NumPy and so on, because you have to use those engines to extract that information. So you will have, for instance, Rasterman, which is based on Postgres, to perform operations that are both on vector and raster with specialized language, and so you can perform a query to extract information such as zonal statistics directly from the database, for instance. without loading at all your raster information, but just providing the required metadata. So what is the set of images where you have to work? What are the polygons where you are interested in, and performing operation in such terms. Okay. This is the final part, but I think that we have seen a lot of things here already. But it is in some way possible, but it is much more limited because Spatial Light is not a database for raster processing. It's a database for geoprocessing for vector, essentially. And it is possible to use another product that is Raster Light, but fundamentally to distribute rasters and vectors and meta information in a compact way. But Raster Light has a very limited capability for what is the processing of rasters. I can remind you, this is a very simple case where I'm simply creating a Raster Light database, which is very similar to a Spatial Light, and populating it with a simple DAM. But the purpose in this case is simply having a compact representation of your information to make a sort of pret-à-porter database to show your information. For instance, within Raster Light 2, you also have a very light VMS server, which is a VMS Lite. You can use to, along with, for instance, QGIS, to show your data, your raster and vector data, all together within a VMS, and show this information in a synthetic way with styling and so on. But it is something much more limited in respect with a proper geoprocessing with both raster and vector components. That's something completely different. So I think to have finished with my brief presentation of the potentialities of SQL geospatial queries and tools. And of course, I'm open for questions by all of you.
So as you can see, everybody, these tools are working mainly with vector data. We didn't tackle much, so that's why we agree with Francesco to present this other application. So mainly, most of the time we work with the raster data for the predictors, but observation and people that are working with census data, for example, population census data or human, let's call it human data set, quite often they come with a really large vector data set. So it's good to have this kind of skills also for dealing with this.
For instance, we at work use a Spatial Light database to represent soil moisture in-field data collected on multiple sites among 16 sites all around the world. Collected for years, every 40 hours or half an hour for whole years. And this is our the component for field data to use with satellite data. And we use the Spatial Light to extract and collect information taken in field for the time interval we are interested in, all over the multiple sites we are working all together, and so having the possibility to perform classification, for comparison, validation, and so on, all possible only by using a massive use of in-field data collected in this way, because the alternatives is simply not practice. You should use tons of multiple format, multiple and multiple instances of different little Excel formats or CSV formats for years and years in multiple sites, something that is not scalable at all in the human life, to perform the same operation of validation with multiple sites and multiple images for long time series. That's the reason, for instance, to use such kind of operation also in the field of remote sensing. That's just to clarify the purpose and the goals of such kind of training and work.